Can you hear me? Well, good evening, everyone, and welcome to this Friends of Imperial Theoretical Physics lecture. What is a theoretical physicist? Well, we don't do experiments. Rather, what we do is twofold. We try and interpret the data that our experimental colleagues collect, but also we try and predict new phenomena that no one has yet thought of. And I hope to cover both of these roles in my talk this evening. What kind of questions do theoretical physicists ask? Well, we like to ask the big questions. How did the universe begin? What is it made of? What are its fundamental constituents? And what are the laws of nature that govern those constituents? And as we look back over the last century, we can identify two pillars on which our theories rest. The first of these is quantum mechanics. Quantum mechanics describes the universe of the very small, atoms, subatomic particles, and the forces between them. And there's a picture of Erwin Schrödinger, one of the pioneers of quantum mechanics. And quantum mechanics is what we call a probabilistic theory, because according to quantum mechanics, we cannot predict with certainty the outcome of any experiment. The best we can do is to assign it a probability. The second pillar on which our theories rest is not probabilistic in that sense. It's what we call a classical theory, and it's Einstein's general theory of relativity. And Einstein's theory applies to the universe of the very large, stars, galaxies, and gravity, which is the driving force of the cosmos as a whole. Now, I think it's fair to say that the layman often uses the word theory in a different sense than the physicist does. You often hear people saying something or other was just a theory. Well, the phrase just a theory is not something one would apply to quantum mechanics or Einstein's general theory of relativity. They've been subjected to rigorous experimental tests and theoretical consistency checks for 100 years now and have passed them all with flying colors. So these are pillars which we are very loath to abandon. And yet, the quandary we face at the beginning of this century is that these two pillars are mutually incompatible. If we try and apply those probabilistic rules to Einstein's theory, it fails miserably. And one can try doing Feynman diagrams. There's a picture of Feynman, and all kinds of terrible things go wrong that I'll tell you about in just a few moments. And on the macroscopic scale, as Stephen Hawking has taught us, black holes threaten the very foundations of quantum mechanics. Whenever these, in the history of science, whenever two principles that we hold dear clash like this, it's often indicative of a new revolution. And many people think that in the theory of quantizing gravity, that this revolution is already underway with the theory of superstrings, which you may have heard of. Now, superstrings, as their name suggests, are one-dimensional objects that can vibrate, just like violin strings vibrate. And each mode of vibration, each note, if you like, corresponds to a different elementary particle. So this note may be an electron, that one a quark, this one a Higgs boson. Instead of having dozens of elementary particles, we have just one string. So it's a very economical way of doing particle physics. One feature of string theory, however, and it's not clear whether this is a disadvantage or an advantage, we'll see, is that they live not in the 3-space and 1-time dimension that we're used to, but rather in 10 space-time dimensions. So the extra 6 would have to be curled up to an unobservably small size, or else rendered invisible in some other way if they're to describe reality. Fortunately, the equations admit solutions where that actually happens. But that was the string revolution of the 1980s, which I'll talk about in just a few moments. But string theory faced its own problems. There was not one string theory, but 5. And in the mid-1990s, it was realized that these 5 apparently different theories were not different theories at all, but rather different corners of a deeper, more profound theory that goes by the name of M theory. M for membrane. And M theory lives not in 10 space-time dimensions, but in 11, which happens to be the maximum, by the way, that supersymmetry permits. So the 11 dimensions of M theory explains the title of my talk this evening, The World in 11 Dimensions. But before we get on to all that, let's go back to basics. If we ask, what is everything made of? A physicist will say, well, everything is made of elementary particles. But what is an elementary particle? In many ways, it's easier to say what it isn't. You and I are not elementary particles. We're composed of smaller constituents, namely molecules. Molecules are not elementary particles because they're composed of yet smaller constituents, atoms. And at the end of the 19th century, it was believed that atoms were the fundamental building blocks from which everything is made. But thanks to Rutherford and others, we discovered that not even atoms are elementary. They're composed of a central nucleus composed of protons and neutrons with electrons orbiting around. And for many years, protons, neutrons, and electrons were deemed to be elementary. But then in the 1960s, we learned that not even the protons and the neutrons are elementary particles. They're composed of yet smaller constituents, the quarks. Now, one could justifiably ask, is this an infinite regression? Will we find that quarks are composed of yet smaller objects, and so ad infinitum? Well, we can't rule that out definitively, but all the evidence, all the experimental and theoretical evidence suggests that the answer is no. That quarks really are the bottom line. They're point-like objects with no further substructure of their own. So let's take a closer look at the quarks, these building block particles, the quarks, together with the leptons, of which the electron is the most familiar example. For reasons we do understand, they come in families, or sometimes called generations. So in the first family, we have what's called the up and the down quark, and a proton is 2 up quarks and a down, and a neutron is 2 down quarks and an up. So 3 quarks make a proton or a neutron. And in the same family is the familiar electron and its friend, the electron neutrino, that occurs in radioactivity and beta decay. And most of what we see around us, most of our terrestrial experience, can be explained by this first family. For reasons we don't really understand, nature didn't stop there, however. There's a second, heavier version of this. There's a heavier version of the electron called the muon, its friend, the muon neutrino, and 2 other quarks that go by the name of charm and strange. And to see these particles, we have to look at more exotic phenomena like cosmic rays. But there's yet a third family, which we've seen only in man-made particle accelerators. But we are fairly confident that that is it. There are just 3 families. And we understand why they come in families. They have to be grouped in this way in order that our theories be consistent. But what we don't understand is why there are 3. That's still a mystery. Why not 4, 5, or some other number? And for each of these particles I've described, there is an antiparticle which has the same mass but the opposite charge. And as is well known, when a particle collides with its antiparticle, they annihilate one another in a burst of energy. So this is, we believe, what everything is made of. But what holds it together? What binds the protons and the neutrons in the nucleus and is responsible for the interaction between the particles? For this, we need to explain the forces of nature, and we believe there are 4 of them. And I've listed them in increasing strength. Gravity is the weakest. Then there's the weak nuclear force, the electromagnetic force, and the strong nuclear force. The strong nuclear force is responsible for binding the quarks and the gluons which into the atomic nucleus, which make at low energies look like protons and neutrons. The electromagnetic force is responsible for all electric and magnetic phenomena, and for light. Light is just an electromagnetic wave. And when we look at the quantum version of light, it comes as a particle. Those electromagnetic waves are quantized in packets of energy that we call photons. And the photon picture was so successful that theorists invented other particles like the photon that go by the name of the gluon and the W and the Z to explain the other forces. And they even invented a graviton to explain gravity at the quantum level. Now, this picture has been very successful. If we augment it with the recently discovered Higgs boson, whose job it is to give a mass to some of these particles, the W and the Z, while keeping the photon and the gluon massless, we get what is called the standard model of particle physics. And since this is about the Imperial College Theory Group, I should mention that it was Imperial's Abdus Salam who was one of the discoverers of this electroweak unification, for which he won the Nobel Prize in 1979, together with Weinberg and Glashow. And I should also mention that although the Higgs boson bears the name Higgs, the mechanism that gives a mass to these particles was developed by several physicists in the 1960s, in particular our own Tom Kibble, who played a pioneering role in explaining not only why the W's are massive, but why the photon is massless. Well, what exactly is a force? Our view of what a force is has changed over the years. As far as the strong, weak, and electromagnetic forces are concerned, we have a very successful picture in terms of quantum field theory. And this picture is supposed to be an example of 2 charged particles exchanging a photon, or it could be a W or a gluon, but exchanging the force-carrying particle. Our historic understanding of gravity, on the other hand, is very, very different. Historically, our understanding of gravity dates back to Einstein's general theory of relativity. And according to Einstein, there isn't a force in the conventional sense of the word for gravity. The reason why an apple falls from a tree, or a planet orbits the sun, or the galaxies recede from one another, is because they're all following a straight line path, but in a curved space-time. So according to Einstein, it's the very geometry of space and time which is responsible for the gravitational force. Very different at first sight from this elementary particle exchange picture. And it's this attempt to reconcile these apparently different world views of what a force is that is at the heart of the difficulty of finding a quantum theory of gravitation. But that's what we need. That's what theorists spend their time trying to find, is an all-embracing theory that will explain all phenomena, black holes, quarks, Big Bang, quantum gravity, you name it. And if our current ideas are correct, and they may not be, I should warn you, this all-embracing theory is going to require three radical ingredients. The first one I've already hinted at, that perhaps our universe has more than the familiar three-space and one-time dimension. The second one is called supersymmetry, and the third one is that we may have to give up the notion that the fundamental building blocks are point-like particles and exchange it for the idea of extended objects such as strings and membranes. So let's talk a little bit about extra dimensions. This is not a new idea. It dates back to 1919 with Theodore Kaluza, who looks like your archetypal classical physicist. And there's a story about Kaluza that his son likes to recall. He belonged to that school of thought that believed that you could arrive at all physical laws by pure reason without resorting to experiment. And to illustrate that, he learned to swim from a textbook. He would lie on the living room couch with the book in one hand, practicing the strokes with the other, and then he walked to the nearest lake and swam from one side to the next. I find it easier to believe in the fifth dimension than I do in the truth of that. Anyway, what was Kaluza's idea? This was shortly after Einstein had developed his general theory of relativity, and Maxwell's theory of electromagnetism had already been around for quite some time. So it was natural to try and find a fusion of Einstein's theory and Maxwell's theory. And what Kaluza suggested was we take Einstein's theory as he wrote it down, but we allow it to have 5 dimensions rather than 4. Now, what do you gain by that? Well, if you, what Kaluza shows is if you look at this 5-dimensional picture from a 4-dimensional perspective, the extra components that a 5-dimensional gravitational field has look like Maxwell's fields. Now, it's not enough just to say they look like Maxwell fields. You have to show that they obey Maxwell's equations. And this was Kaluza's miracle. If you plug in the 5-dimensional metric into 5-dimensional Einstein equations, what you get out are the 4-dimensional Einstein's equations plus Maxwell's equations. So Maxwell's equations, Maxwell's theory of electromagnetism comes for free if you're willing to buy the idea of a fifth dimension. Now, 2 obvious questions are, if there's a fifth dimension, why haven't we seen it? And a second question is, do the fields depend on the 5th coordinate? Because for reasons he didn't explain, Kaluza said they didn't. He just allowed the fields to depend on 4 of the 5 coordinates. Well, an attempt to cure both of these problems came a few years later by Oscar Klein, who said, let's suppose there are indeed 5 dimensions, but the 5th one is not like the other 4. It doesn't stretch from minus infinity to infinity. Rather, it has the topology of a circle. So if you set out in the 5th direction, you come back to where you started. And this is an attempt to illustrate this. It's hard to imagine, I think you'll agree, a universe with where at every point in 4-dimensional space-time there's a little circle. But we can imagine a 2-dimensional analogy. Let's look at this tightrope. If we stand sufficiently far away from it, it looks like a 1-dimensional line. Closer inspection, however, reveals that at each point of the line, there's a little circle. And a small enough creature like an ant could go in the direction right angles to the tightrope walker. That's the analog of the 5th dimension. And the virtue of taking the fifth dimension to be a circle is that it explains, or it is an attempt to explain, why electric charge is quantized. Because in this picture, electric charge is just the fifth component of momentum, but if you have momentum in a circular direction, it comes in integer lumps. So that was the first attempt to go beyond the 4 dimensions. But it was revived when along in the 1970s, when along came something we call supersymmetry. We've seen that there are 2 kinds of particle. On the one hand, there are the building block particles, the quarks and the leptons, which collectively we call fermions. They have a property called spin, which comes in half integer units, spin half, spin 3 half, and so on. The other kinds of particle are the bosons, of which the force-carrying particles are bosons, and they have integer spin, 0, 1, 2, and so on. And it was believed, up until the early 70s, that in attempts to unify different particles and put them into families and groups, you could never combine bosons and fermions. But that turned out to be a false belief, and supersymmetry does exactly that. It's a way of unifying bosons and fermions. If you write down your equations and you swap the bosons for the fermions and the equations stay the same, you say that they're supersymmetric. And supersymmetric theories have some wonderful properties that the theorists love. We'll come to whether the experimentalists love them in just a moment. One implication of supersymmetry is that for every particle we know, the electron, the quark, the Higgs, and so on, there is another particle with the opposite statistics. For every boson, there's a fermion. But we don't see these particles with the same mass. So clearly, if supersymmetry is a symmetry of nature, it must be what we call a broken symmetry. And it must be broken at energies higher than we've been able to achieve with our most powerful accelerators, because to date, we haven't seen these superpartners. So that could mean that they don't exist, or it could mean that their masses are greater than we've been able to achieve in the laboratory. But one of the reasons why, certainly why I became interested in supersymmetry and why 40 years on, theorists are still working hell for leather on supersymmetry, is because supersymmetry implies gravity. It turns out that if Einstein had not already discovered the general theory of relativity, supersymmetry would force us to invent it. In a certain technical sense, a supersymmetry transformation is the square root of a general coordinate transformation, and it's the general coordinate transformations which are at the heart of Einstein's theory. But there was an unexpected consequence of supersymmetry, and that is that it places a limit on the dimension of space and time. The mathematics of supersymmetry simply doesn't work in dimensions greater than 11. Now, it's hard to give a hand-waving reason for why it's 11 and not some other number. I won't try. But there you have it. If supersymmetry is a symmetry of nature, nature cannot have more than 11 dimensions. And in fact, it's in that 11th dimension that the equations of supersymmetry take their simplest and most elegant form. And in the early 1980s, this led people to think that perhaps this 11-dimensional supergravity theory might be the theory we were looking for. And indeed, it admits solutions in which not 1 dimension, but 7 dimensions are curled up, a la Kaluza and Klein. Now, Kaluza and Klein were thinking of a circle, so the simplest generalization would be 7 circles. But it turns out you're not limited to just 7 circles. You could have a 7-dimensional sphere. And in fact, the mathematicians have dreamed up infinitely many 7-dimensional spaces that could act as the extra dimensions of this theory. And each different choice gives you a different four-dimensional theory. Now, some choices look good. They give you the right photons and W bosons and Z bosons of the standard model. But unfortunately, as Edward Witten pointed out, this, in its most naive formulation, can never explain the fermions of the standard model. And one reason is that nature distinguishes between left and right. It turns out the left-handed quarks and leptons behave differently from the right-handed ones, and this can never be explained in this simple framework. But there was another reason why 11-dimensional supergravity, or indeed any supergravity, was never going to be the final answer. And that has to do with this incompatibility of quantum theory and gravity that I mentioned at the beginning. And it comes down to what happens at short distances. In conventional quantum field theory, we think of particles interacting at a point. And that point-like nature gives rise to infinities. When you try and compute the probability of one process, one initial state evolving into another, you get nonsensical answers, which, however, can be made sensible by a process called renormalization. And for the strong, weak, and electromagnetic forces, that idea works very well, but it fails for gravity. And the conclusion one has to reach is that for gravity, we have to give up this point-like idea and replace it by something else. And this is where strings came in. Strings can either be open, like this, or they can close on themselves to form a loop. And if you imagine two loops colliding, as opposed to two particles colliding, instead of this sharp corners, you get a smooth structure. And it's the sharp corners that gives you the infinities. So it was speculated that if we replace point-like objects by strings, we could eliminate the infinities, and in that way, perhaps get a consistent quantum theory of gravity. And in the 1980s, in the 1984 superstring revolution, that's what happened. A consistent quantum theory of gravity was found by looking at the right kind of supersymmetric strings. And everyone went bananas. They thought this was perhaps the answer to all our prayers. So as I mentioned at the beginning, the vibrating modes of a string, here's an open string, here's a closed string, represent the elementary particles, and crucially, one of the particles they describe is the graviton. So gravity is built into string theory. You don't have to impose on it. It's there from the very beginning. But there were not one consistent 10-dimensional string theory. There were 5. These are their names. Their names are not important. The important thing is there were 5 rival theories for this theory of everything, which is an embarrassment of riches, of course. We'd like just one theory of everything. Now, other puzzles. I said that supersymmetry says that nature cannot have more than 11 dimensions. So why should we stop at 10? It seems rather perverse. And a related question is, if we are going to give up 0-dimensional objects for 1-dimensional strings, why stop there? Why not 2-dimensional membranes or higher dimensional objects? And this is what we called naught branes, 1 branes, 2 branes, and inevitably p branes was the general case. So a particle in this language is a naught brane, and as it evolves in time, it sweeps out a 1-dimensional line. A string is a 1 brane, and it sweeps out a 2-dimensional surface as it evolves in time. And so on, a membrane looks like that. Now, what kind of branes are allowed. By the way, I can't help resist pointing out that the first use of the word brain, according to the Oxford English Dictionary, was in a paper I wrote with colleagues here in the theory group at Imperial College. What brains can you have? Well, here's a picture we call the brain scan. And we've plotted vertically the dimension of space-time and horizontally the dimension of the brain. So little d is p plus 1. Now, in the 80s, Green and Schwartz taught us that strings, which are d equals 2, can live in dimensions 3, 4, 6, and 10. But only the 10-dimensional ones were quantum mechanically consistent. When we allow for other objects, something interesting happens. We find that these 4 strings are just the limiting cases of 4 sequences of extended objects. And in particular, the quantum mechanically consistent string lies on a sequence with an 11-dimensional membrane. So this, to some of us, seemed the answer to the question, why do strings live in 10 when nature, in the sense of supersymmetry, allows 11? Well, strings live in 10, but membranes can live in 11 dimensions. Moreover, you say, well, what's the relation between the two? If you imagine the 11th dimension to be curled up in the way Klein suggested, and you wrap the membrane around it, then provided the circle is sufficiently small, if I had a sheet of paper, I'd roll it up for you, and you'd see that provided it's sufficiently small, what started out as a membrane in 11 dimensions ends up looking like a string in 10 dimensions. In fact, it's just one of those 5 consistent string theories, the TAC2A string. So this suggested to us that perhaps membranes were as important, if not more important, than strings were. But of course, there were skeptics, and one's reminded of the, I don't know if any of you have read this charming book by the Victorian clergyman Edwin Abbott, but the hero of his book, Flatland, was Mr. Square, Mr. A Square, there he is, who lived in a 2-dimensional world. And he was astonished one day when a creature from the 3rd dimension, Mr. Sphere, passes through his plane. He sees a circle which grows and shrinks. And Mr. Sphere explains to him that there's more to life than the 2-dimensional world that Mr. Square inhabits. And Mr. Square is, of course, very skeptical. And so it was that the 10-dimensional string theorists were reluctant to accept the membrane theories from the 11th dimension. And so between the string revolution of 1984 and the year 1995, there's a cartoon which I know you've got charm, but I'm really into brains. This was the state of affairs until 1995. There were a group of people working on 11-dimensional supermembranes. There were a group of people working on 10-dimensional superstrings. And it wasn't clear if they were on the same page or what. And then came along the 1995 M-theory revolution, where Edward Witten discovered that they were not 5 different string theories and 11-dimensional supergravity. There was just one theory, which he called M-theory, and all these other theories were just corners of this more profound framework. To illustrate how mathematical things get, I should tell you that although Witten is a physicist, he won the Fields Medal for Mathematics, which is the Nobel equivalent for mathematicians. And trying to keep up with string theory nowadays requires some sophisticated mathematics. But it was Witten who said M stands for magic, mystery, or membrane, according to taste. And understanding what M-theory really is would transform our understanding of nature at least as radically as occurred in any of the major scientific upheavals in the past. A few years ago, by the way, Witten was voted by Life magazine as the 6th most influential American, more influential than Bill Gates, who came 7th, though not quite as influential as Oprah Winfrey, who came 5th. So there's another illustration of physics at the crossroads. And I should add that the members of the theoretical physics group here at Imperial were amongst the pioneers of M-theory and continue to do work at the forefront of the subject. And here's a picture of the friendly faces. Now, this brain world has some other consequences. Kaluza and Klein were thinking of small extra dimensions, but the theory allows big extra dimensions. In particular, you can imagine a situation where our universe is itself a three-dimensional brain in a higher dimensional bulk. An analogy would be that we're the slice in a loaf of bread, but there are other slices parallel to ours, parallel in the 5th or higher dimension. And in this scenario, the strong, weak, and electromagnetic forces attract on the brain. They don't leak out into the extra dimensions, but gravity does. So this world interacts with this world only by gravity. Now that should ring a bell, because we believe that most of the matter in the universe is dark matter that interacts only gravitationally and is not of the kind familiar protons and neutrons that we're familiar with. And there have been speculations that perhaps these parallel universes could be the origin for the dark matter. That's very speculative, by the way, but it's a nice idea. So where are we? Let's summarize. In the 1830s, Faraday and Maxwell, others, realized that electricity and magnetism were not really two different forces. They were part of a single electromagnetic force. And then in the 1960s, Salam with Glashow and Weinberg unified the weak nuclear force with the electromagnetic force to form what we call the electroweak force. Well, the obvious logical conclusion then is to try and combine the strong nuclear force, and this is what George I. Glashow and others did, into what we called grand unified theories. But you notice the color of the ink has changed here, because to the right is still theoretical speculation. To the left, it's all experimentally well established. So one should bear in mind what's what. But anyway, grand unified theories have a lot going for them. They predict things that you wouldn't see otherwise, such as proton decay, magnetic monopoles. They haven't yet been seen, but that doesn't mean the theory is wrong. It could mean that we need more powerful detectors, more powerful accelerators. And then Green, Schwartz, and others in the superstring revolution put everything together into these five different 10-dimensional string theories. And then in 1995, along came M-theory, and I've put Witten's picture, but there are lots of other people who contributed to it. And the question now is this the final theory, or have we painted ourselves into a corner? What's going on? M-theory is an ambitious attempt to answer all the big questions, but there's a certain sense in which it's a victim of its own success. What do I mean by that? It's to do with curling up the extra dimensions. I mentioned that there were mathematicians can think of infinitely many ways of curling up the extra dimensions. And each different way gives you a different looking universe. Some of those universes look like the universe we live in, with 3 families of quarks and leptons, and with the 4 fundamental forces. Others look nothing like our universe. They have too many families or no families, or they have different kinds of forces. But from a mathematical point of view, they're all perfectly good solutions of the equations. This is called the string landscape. And the question then is which, if any, describe the world we actually live in. And this has divided the theorists, you might say. The traditional view is one of convergence, that the more we understand about the world, the more we will realize that the ultimate theory is unique. And the question that Albert Einstein asked, did God have any choice in creating the universe, would be no, according to this traditional picture. And if we're clever enough and smart enough, we'll eventually narrow down the ultimate theory to just one, and that one will be the world we find ourselves in. The alternative view, which is gathering more momentum, I would say, is the multiverse. But all of these different mathematical possibilities are indeed mathematical, not only mathematical possibilities, but physical realities. There are infinitely many different universes with all kinds of different properties, and we just happen to be living in one of them. And one of the arguments that proponents of the multiverse put forward is that they note that the universe we live in is in a certain sense bio-friendly. If we were to take all the fundamental constants and try tuning them or dialing them to different values than we actually have, we would find that you don't have to tweak it very much before life as we know it would not be possible. For example, in some universes would expand so rapidly that no galaxies could form. Others would collapse on themselves too quickly for life to have formed. The kind of universe that breeds people like us is very special. Now, again, one can take 2 views on this. Maybe there's a fundamental reason. Maybe that's just the way it is. But the proponents of the multiverse like to invoke bio-friendliness by simply saying, well, this is the universe we happen to find ourselves in. And of course, to us, it appears to be just right, the Goldilocks enigma. There are lots of other universes where we don't inhabit, and the creatures of that universe would think the same that we do. One of the most vocal proponents of the multiverse is Steven Weinberg, that Jerome referred to earlier this evening. And he goes as far as to say that these discoveries lead to changes in how we score our work and in what we consider to be an acceptable theory. So for Weinberg, this is a whole new way of doing physics. By contrast, another Nobel laureate and string theorist, David Gross, hates the idea. And he's fond of quoting Churchill, never, never, never give up, because he reviews the landscape idea as a cop-out. Another proponent is our own astronomer at Royal Lord Rees, who with typical eloquence says the universe in which we've emerged belongs to the unusual subset that permits complexity in consciousness to develop. Once we accept this, various apparently special features of our universe, those that some theologians once adduced as evidence for providence or design, occasion no surprise. So the debate rages on. The multiverse idea is in a certain sense bucking the trend towards convergence. For example, I said that the quarks and leptons have to come in families, and that meant that in the 90s there had to be a top quark that had not yet been discovered if this picture was right, and sure enough, the top quark was discovered. It's that kind of reasoning that tends to think that we are converging on a unique picture, but the situation in string and M theory is that we are finding more and more possibilities. Maury-Gell-Mann summed it all up. If we really live in a multiverse, physics will have been reduced to an environmental science like botany. And he wasn't being polite to the botanists. Now, a question which everyone wants to know the answer to is M theory testable? Well, we've seen there are certain generic features, supersymmetric particles, extra dimensions. I didn't have time to tell you about microscopic black holes, cosmic strings. And if we're lucky, some of these might be seen at the next generation of accelerators or astrophysical observations. CERN's Large Hadron Collider has confirmed the existence of the Higgs boson, but so far it's not seen any supersymmetry. Now, does that mean that supersymmetry is wrong, or does it mean that the superparticles are heavier than they've managed to achieve in Geneva? It's hard to say. The Planck surveyor did sterling work, but I think the summary was business as usual. Just recently, the BICEP detector has confirmed the existence of gravitational waves, which is evidence for the idea that the universe underwent an exponential expansion shortly after the Big Bang. So these are all consistent with M theory, but they don't confirm M theory. And it's this lack of uniqueness of the landscape that's preventing us going to our experimental colleagues and saying, here's a unique prediction, go and test it, and then we can falsify the theory. We're not yet in that situation. Now, some people have said, if you're not making rapid predictions that can be compared to experiment, you're not doing science. But I think that's a wrong view of the history of science and the way theoretical physics develops. Even if we stop tomorrow, let's say we abandon string theory and M theory, sharpened our pencils and say, well, where do we go from here? The landscape problem would not have gone away. The issue of why we choose one mathematical universe, one physical universe from an infinity of mathematically possible universes, is one that any attempt to find a final theory is going to have to confront. And at the moment, no one has an answer. Just to illustrate the timescales, black holes were first proposed in the late 1700s, but it wasn't until 1916 that they were put on a firm foundation by Karl Schwarzschild in Einstein's general theory of relativity. And Oppenheimer and Schneider pointed out, Einstein didn't take it seriously, by the way, but in the 1950s, 30s, Oppenheimer and Schneider pointed out that when a star burns up its nuclear fuel, it will start to collapse, and if it's sufficiently heavy, it will inevitably form a black hole. And it wasn't until the 1970s that observational evidence for black holes began to accumulate, and now, of course, everyone believes in black holes. Quantum entanglement is another thing proposed in 1935, but it wasn't until the 1960s that John Bell came up with a falsifiable prediction, and it took another 20 years before that prediction was tested experimentally. So the point I'm trying to make is that all theoretical ideas have a gestation period. There's a time lag between the germ of the theoretical idea and the experimental confirmation, and I just listed a few obvious examples, and here are some predictions that have not yet been confirmed. So I think the answer is you work on whatever you think is the most fruitful direction, and you shouldn't impose any artificial deadlines on how long it's going to take to find an empirically falsifiable prediction. I should also add that string theory has undergone some various transformations over the years. Its most famous manifestation is of the one I've discussed this evening as a candidate for a theory of everything. But more recently, thanks largely to Juan Maldacina's ADS-CFT correspondence, applications of the string techniques have found applications in other branches of physics: superconductivity, cosmic strings, fluid mechanics, quantum information theory. And these largely serendipitous discoveries will be testable in the shorter term, but they would never have come about if the critics, the stop string theory critics, had had their way. So let me finish then with an example of applying string techniques to entanglement. My colleagues Borston, Hanayaka, Marani, Rubins, we showed how you could use string theory techniques to describe how 4 qubits are entangled, something which hadn't previously been enunciated. And I'd like you just to bear in mind some equations that I've taken from the paper and pose the question, are there implications for the Big Bang theory? Because, and I don't know if you can notice, if you look at the blackboard here, it's not very clear. You'll find exactly the equations from our paper. And I have to congratulate the scriptwriters because they got it exactly right. So let me finish then. Is M-theory really the final theory? I think the best answer is to recall the answer that Chairman Mao gave when someone asked him, "What do you think of the French Revolution?" And he said, "It's too early to tell." Thank you very much.
Thanks, Mike. Do we have some questions before we go upstairs for some refreshments? Just here. Thank you. Yeah.
Shall I just begin?
Yes.
The M-theory landscape. If we take the subset of the landscape that would predict exactly what we know of physics, there is such a landscape?
Well, that's a good question. Is there one that gives us, never mind the others, is there one that works?
Exactly.
And so far, not quite. There are ones. The problem is there are certain technical questions, like how do you break supersymmetry, that our current understanding of M-theory has not yet answered. So you have to supplant what we know for sure with guesses of what would happen if only we understood the theory better. And that's where the, can we do that and get one that looks just like the standard model? The answer is not yet. You can get 3 families of quarks and leptons, you can get the Higgs, you can get all the standard model particles, but explaining the coupling constants and the other mixing angles and all that sort of thing, we've not yet managed to do. Now, it could be that there's some manifold that we haven't yet thought of that does it, or it could be that there's some other way of going about it.
I mean, it could be that there's something other than M-theory.
Oh, it could be, yeah, there could be something other than M-theory. One has to entertain that possibility. But it could also be that there's some other manifold that we haven't yet thought of.
Yes.
At the moment, we can't do Yang-Mills non-perturbatively. But suppose somebody did do that. Do you think that might, do you think the techniques developed in that?
Do I think, could you repeat the beginning? You said Yang-Mills?
If you could solve for Yang-Mills non-perturbatively,
Yes.
do you think
That would be, it might be very helpful, yes, because my personal view, my own personal view, is that we will never make contact with the experiment until we understand the theory better than we do at the moment, and that it's premature to be making predictions of what's going to happen at the Large Hadron Collider. That's my own view. And the problem is, the root of the problem is solving non-perturbative equations of M theory. So if there was an example of, such as Yang-Mills, that we could solve non-perturbatively, that may well point the way. That might be very helpful, yes.
One more question, yes.
Comparison, I know that I think some people have said that maybe string theory has had too much resource. Such as loop quantum gravity. I just wonder whether...
In my experience, I take a sort of Darwinian view that it's the survival of the fittest. The brightest young people will work on whatever they find most exciting. And it's where they decide to work and the success they have in those directions that explains the funding. And if they're having lots of success and getting lots of exciting results, the funding will go in that direction. So, in a way, arguing about, well, it should be going here or it should be going there, it takes care of itself, in my view. And so long as the brightest young people continue to work on string and M theory, it will thrive. And if they find that it's not going in the right direction, or they're coming up against down a blind alley or a brick wall, they're very smart. They'll move on to something else. So if loop quantum gravity or these alternatives offer them a better route, they take it. So I'm relaxed about the way that works, with one proviso, as Jerome mentioned. The people who pull the strings, if you pardon the pun, the purse strings, like the EPSRC, have their own idea of where theoretical physics ought to go. And that's a dangerous precedent.
Question over here.
You mentioned that BICEP 2 may have discovered gravitational waves, but there is an observation by Holson-Taylor, the energy loss in a binary pulsar running down, and many regard that as a sufficient proof of the existence of gravitational waves. Do you believe that is the case?
I agree with you, totally, yes. The Holson-Taylor result that the binary star system was losing energy in exactly the way that Einstein's would have predicted as loss due to gravitational radiation is a very convincing argument for gravitational waves, but it's an indirect argument. The analogy I would use is discovering neutral currents was indication of the Z and the W, but it wasn't until we actually saw the Z and the W that we knew they were there. And I would put the Hulse-Taylor gravitational waves in the same bracket. It was almost certainly that we were going to find them, but it wasn't until BICEP that we actually did find them.
What I suggest at this point is that we adjourn to go upstairs, where we have some refreshments on the 8th level. And one of the reasons I suggest that is that we do have a deadline, which is 9:30. So at 9:30, we have to end the proceedings. And one of the reasons is that you can be locked in the building. And as much as you might be fans of Blackhead, to spend the weekend here, I can assure you, is not so exciting. So we have to finish at 9:30. The lifts are just outside. There'll be a flow of people going up to the 8th floor. And one more press point is that there are members of staff, some postdocs and students who will be up there, and we all have name tags on. So if you want to speak to a local about anything, just seek them out and please do. But before we leave, let's give Mike a big round of applause.